Welcome to this primer on graphs. We will continue our discussion from last time, and let us recall the definition of a graph. So a graph is a pair V, E, where V is a set, non-empty set. Non-empty and finite, typically finite. I mean, for us, it will always be finite, I think. But there is nothing wrong with V being infinite. But all the graphs that we will consider will be on finitely many vertices, so to say, unless explicitly mentioned otherwise. So V is a non-empty set. And what is E? E is a collection of two-element subset of V. So each element in E is a two-element subset of V. When we say two-element subset, we mean a subset of size 2. Okay, and we saw that one can pictorially represent any graphical data. So let's say we have these three vertices. So the things here are called vertices, or V is called the vertex set, and these are called edges. We discussed that. And suppose we draw a figure like this. This is trying to suggest the graph, which I'm going to write down, where the vertex set is this three-element set, and edge set is 1, 2, and 2, 3. Alright, so I hope so much is clear. And now let us move on. So in this lecture, we'll just look at the definition of what is called a bipartite graph and look at examples. So a graph G, again, finite, everything we will define for finite graphs. A vertex set V and edge set E is said to be bipartite if, actually you don't need any finiteness in the definition. So it is said to be bipartite if there is a partition A comma B of V. I will explain what this means, but let me write down the full statement. There is a partition A comma B of V such that for any edge A, one endpoint. So we haven't defined endpoint, but I will do so here. One endpoint of E lies in A and the other lies in B. Just so that there is no confusion, I will replace this with every. That is what I meant anyway. So it's not clear. First, we have to define what this is. First of all, what is a partition of V? When we write this phrase, what we mean? We mean two non-empty subsets, first of all. Two non-empty subsets A and B, such that their union is the entire set V and their intersection is trivial. So if, let's say, this was V, then A could be this part and B could be the remaining part. So natural definition of partition, we discussed this in functions primer or maybe relations primer. Yeah, in relations primers. So yeah, that's what we mean by this phrase. And endpoint. So this we need to define properly. So if E is this edge, let's say x comma y, then x and y are called endpoints. So that's the definition of endpoints. Oops, it looks bad. So it's a good terminology, because if you look at the picture, let's say this graph, and you take this edge, these two do look like endpoints visually, so it's a good terminology. Right, so what we are saying is, a graph G, let's say this blob denotes the vertex set. Usually vertex sets are denoted by dots, but blobs are also a very popular way to depict vertex sets of graphs. So this whole blob thing is denoting the vertex set. So we will say G is bipartite if one can find a partition of the vertex set into two parts, such that whenever we pick an edge, we find that one endpoint is in A and the other is in B. Right? So the definition should be clear, but generally, one can picture a bipartite graph as follows. It is going to look something like this. So all the edges will be crisscross. These are all vertices. Right? So there will be no edge which is going across A, two vertices in A, and there will be no edge that will be going across two vertices in B. So if you can find such A and B, then you declare the graph bipartite, and there is no clause of uniqueness here. There could be multiple such A and Bs. That is completely fine. If you can find one such partition, you declare the graph bipartite. Okay, so now given a bipartite graph, a bipartition of the graph G is a partition of the vertex set such that, again the whole thing I have to write again, such that maybe I'll copy it. Right, so a bipartition of G is a partition A comma B of V, which witnesses the fact that the graph is bipartite, such that for every edge in E, one endpoint of E lies in one part and the other endpoint lies in the other part. Okay, so that's the definition of bipartition. So a graph is bipartite if and only if you can find a bipartition. You can say it that way. Okay, so I hope this was clear. And now let's move on to examples. So first example, this is patently a bipartite graph. Here we have already been given a bipartition. The vertex set is 1, 2, 3, 4, 5 vertices, and these are the edges. So one can formally write this down, but there is no point. And then there is this example, which is not immediately suggesting its bipartiteness, but it happens to be bipartite. So how do we see that it is bipartite? So color these vertices, color this with pink and color that with pink. Now this set of pink vertices do not have any edges within themselves. Every edge that you see coming out of a pink vertex is going to a white vertex. And same for the white vertices. There is no edge that you can find between white vertices. Every edge that comes out of a white vertex lands on a pink vertex. So the pink vertex or the pink vertices together and the white vertices together form a bipartition of this graph, and hence this graph is also bipartite, even though it wasn't drawn explicitly so. Okay. Now lastly, here is a graph that is not bipartite. I mean, you can just try. You can try all the partitions. This could be one attempt, and all the other attempts are going to look very, very similar because of the symmetry of the situation. But suppose you make this attempt, so this is one part and this is the other part, then within this part there is already an edge. So this is not a bipartition, and similarly any other thing will not be a bipartition. Okay, so these are some examples of bipartite graphs. We will continue our discussion with this concept, but for now this is enough. As usual, like, comment, share, subscribe, and I'll see you next time.